at CWI before that, and before that he was a student of Arkady Nemirovsky at Georgia Tech. And he will tell us about fast deterministic and sparse dimensionality reduction, like all for the price of a single algorithm.
Well, yeah. So thanks, Vitaly, for the introduction. Yeah, I'm very happy to be here and talk about this work. Yeah, so basically it's some work we did in collaboration with Daniel Ladouche and Neil Olver, both from Amsterdam. And this is going to appear soon in SODA. So let me talk first about what do we mean by dimensionality reduction, more precisely in the setting of our work. So, okay, so the basic idea is quite simple to explain. We have a set of high-dimensional vectors, V1 through Vn, in Rd. So the way I like to think about this is D is a rather large dimension you're working with, but the number of vectors you have is even larger. So that's the kind of region we're interested in. So yeah, we want to map these to a lower dimensional space, and of course we don't want to do this in an arbitrary way. We want to do it in such a way that we can maintain distances approximately. Right? So if these are the original distances, it's Vi minus Bj squared in Euclidean norm, then we want our output to be within a 1 plus minus epsilon approximation factor. Okay, so the idea, you can see it in this very simple picture. For instance, you have two vectors in the unit sphere, right? So there's one way to find a projection which maintains its distances exactly, which is basically taking a two-dimensional plane that contains both the origin and these 2 points. But the point is that many hyperplanes can maintain these distances approximately. So you can see here a few examples. And indeed, this kind of slack we have gives us freedom to do this projection with many more vectors at the same time.
So you allow the mapping to be data dependent?
Yes, in our case, we will. So I guess you're thinking about these oblivious kind of constructions. I mean, our setting is not about that in particular, but it's also very interesting.
So another question. So is M here fixed, or are you going to pick M based on the data as well?
Oh, yeah. I mean, we want to make M is going to be dependent on N and epsilon, but not on D. Okay, so a few things which are highly desirable, of course. If we can make this mapping to be linear, this is very helpful. For instance, it allows us to simplify slightly bit the kind of flow distortion property by just, instead of looking at differences or distances between points, we can just look at maintaining norms of certain vectors, where these vectors, of course, are the differences. And on the other hand, I mean, we would like to find some kind of projection pi, which is very easy to compute. So for instance, if this matrix pi is very sparse, or it's highly structured based on some kind of Fourier transform, then that's highly convenient. So just to mention a few applications on how this technique can be useful. I mean, there are a number of applications. I'm not going through all of them, but I'll just kind of show you a couple so you get an impression on how these things are used. So for instance, for the case of binary classification, we suppose we have a data set with labeled examples, positive and negative here. And there's typical this assumption in machine learning that you can separate these positive and negative examples with a certain hyperplane, which not only separates them, but it does so with a certain slack. So there is some margin gamma where you're guaranteed that you don't have any input vectors. And somehow this guarantee of having this margin is in a certain way a certificate that our solution is in fact quite structured, quite simple. What you can do is take any of these sort of dimensionality reduction techniques, map these vectors to a lower dimensional space, and since you're approximately maintaining distances, basically you can highly reduce the dimension of the problem, losing a little bit on slack on this margin, just a constant factor. So and extending the separator to the high dimensional space is trivial. You just extend it by zeros. So a second more involved example is the case of nearest neighbors. So here we have a large data set V1 through Vn in Rd. And for a certain vector Vi, and for a certain parameter k, we want to know what are the k closest elements to Vi. And we can also ask the same question about approximate nearest neighbors. So the issue here is that there's, of course, a naive algorithm that would go through all of these input vectors, compute distances, and keep the the lowest ones, the closest, but that's expensive, right? Particularly if we're thinking that D and N are rather large, that's an issue. So there's this sort of classical idea of somehow pre-processing the system instance, coming up with a nice sort of data structure that would allow us to make queries in much faster time. The issue is that this pre-processing typically will run into an exponential in the dimension complexity. So that's what's known as the curse of dimensionality. And the way that this has been fixed, and this is the classical work of Indicat Mode 1, is that basically you can first project these vectors using some low distortion embedding. You maintain distances approximately, and then you can do the pre-processing efficiently, because basically what you end up paying in terms of the projection dimension is logarithmic in the number of points. So we will see that in a bit. So, OK, now let's go into the more technical aspects of this talk. I'm going to first talk about the classical Johnson-Lindenstrauss lemma, and then we'll go and improve these things bit by bit, so including these fast, deterministic, and sparse one by one. So, yeah, so the classical result, known as the Johnson-Lindenstrauss lemma, basically says the following. So the high-level idea is that we want to come up with a construction of a matrix pi, which is random. And our guarantee is going to be a certain probability of having high distortion with respect to a fixed but arbitrary vector p. So it's phrased in a slightly different way to what I was saying in the beginning, right? But you can imagine, I mean, it's easy to turn this into a guarantee for multiple vectors. So the point I want to emphasize here, and something that I said before, the projection dimension m scales with epsilon as 1 over epsilon squared. And if we have a certain confidence parameter delta we want to control, we'll be paying a log of 1 over delta in the projection dimension. Okay. Is this statement clear? Okay. So how do we handle multiple vectors? Well, it's just a matter of taking.
One question. So random matrix here means what? Random over what?
Well, for now, I'll just say random. In a bit, I will explain which specific constructions we care about. So if you want to handle multiple vectors in the setting I described in the beginning, you can just take a union bound on this, right? So if you care about maintaining norms of vectors v1 through vn, and you want to have a constant confidence, you can make this projection scale as log n over epsilon squared. And what kind of distributions we care about? Well, so first of all, the classical result of Johnson-Lindenstrauss shows that if you pick this projection as a projection on a random subspace, this will work with high probability. Of course, this is not very efficient, of course, because you need then to compute this projection according to the subspace. So the work of Indicat Mode 1, what they did is show that you can make this much simpler. You can just pick IID Gaussian coordinates, and this will work with the same kind of probability guarantee. You can make this even more efficient, and that's the proposal of Aklioptas, which is basically picking IID coordinates Rademacher. So plus 1, minus 1 equiparably. Right? And then you need to, in both of these cases, both the Gaussian and the Rademachers, you need to somehow rescale properly. So basically, you want to make the variance of the same scale as 1 over m, because the height of your matrix is m. And all these analysis of these high probability bounds are based on this idea of concentration of measure, which I will go into now. So the natural notion of concentrated random variables will look here. It's the notion of Sub-Gaussian random variable. So the definition of a random variable being Sub-Gaussian with a certain Sub-Gaussian parameter nu is that basically the moment generating function of x, it's upper bounded by the moment generating function of a Gaussian with variance equal to nu squared. Okay. So some examples, of course, a Gaussian is Sub-Gaussian with the Sub-Gaussian parameter being the variance, but also the Rademachers are 1 Sub-Gaussian. So the picture looks a little bit like this. Things which are highly concentrated. So if you look in black here, this distribution of a Gaussian random variable, a Sub-Gaussian is better concentrated around the origin. And something which is not Sub-Gaussian will typically have this kind of kink here at the origin. So let me ask at this point, are you all familiar with the proof of the Chernoff inequality using Sub-Gaussian random variables? No? Should I take a moment and do it? It's going to take just 1 minute, and I can do it on the board. So basically, under that assumption, I can prove that the random variable will concentrate well. So if I want to control the probability of x being larger than a certain threshold t, I can just use the monotonicity of the exponential here. Right? And even further, I can write this as a quotient of this being larger than 1, right?
Maybe a different marker.
Yeah.
Try another one.
Let's see. So, oh, this is much better. E to lambda x divided by lambda t larger than 1. So what we can see here is we're basically integrating something which takes value 1 when this inequality is satisfied, and it's 0 otherwise. So just using Markov's inequality, I can upper bound this by and now in position to use the Sub-Gaussian property, dominating this thing by the moment generating function of the Gaussian. So I have a 2 over there, yes. And then, I mean, it's just a matter, all I need here is that the lambda is positive. So then I can optimize in terms of lambda. And this is, on top here, we have a quadratic, sorry, this should be lambda squared, mu squared. So this is quadratic in lambda, we can optimize it and we'll get concentration of order e to the minus, I think it should be t over 2 mu squared if you optimize this thing. So that's why we care about the Sub-Gaussian random variables and why they give us concentration. So any questions at this point? Good. Okay, so unfortunately what I want to talk about now is something which is more involved, which is basically concentration for quadratic forms. So this is the so-called Hanson-Wright inequality. So the setting here is quite similar in principle. We have a vector of independent new Sub-Gaussian random variables, and we have the symmetric matrix which has 0 coefficients in the diagonal. Okay, the assumption of 0 coefficients in the diagonal is not important for the result to be true, but it's going to help us a lot, and it's always satisfied in the setting of Johnson-Lindenstrauss. So basically, what we have under these assumptions is that this quadratic form, x transpose ax, is going to concentrate at this rate. And this rate is an expression that looks slightly complicated. It depends somehow on the operator norm of A, on the Frobenius norm of A, and it has these two kind of behaviors. So let me make a plot a little bit so you can get a handle on how this looks like. This term in blue here is a Sub-Gaussian kind of tail. So it looks like this over here. And the other one is just a kind of an exponential decay in t. Okay, so you have this kind of behavior. And basically, this minimum is picking the worst of both in each region. It's still an exponential concentration, it's just not as strong as Sub-Gaussian. And from now on, I'm not going to care much about this new square term, because we mostly care about the case of the Rademakers, which are one Sub-Gaussian. So you can completely forget about the new.
Sorry, question. Can you just go back? What was A again?
A is a matrix that it's a symmetric matrix which has 0 coefficients in the diagonal.
Right. Okay.
So think about the case of the Rademakers. Well, these diagonal terms are just multiplied by this sigma squared, which are always 1. So that's a deterministic term.
Right.
Okay, so now I'm going to show you briefly how you can prove Johnson-Lindenstrauss based on this concentration of quadratic forms. This is a proof due to Kane and Nelson. So the setting of our projection matrix is what I said before. We'll pick IID Rademacher coordinates, right? And we'll scale them by 1 over square root of the height of this matrix, so the number of rows. Now, for notational purposes, I mean, this is the random object I want to study. It's a matrix, and I want to write it as a quadratic form, so I need to write it in vector form. And to do that, I'm basically just stacking the rows of this matrix. And that's what I defined as sigma. It's just a vectorized version of pi. Well, now, let us know that the kind of low distortion property that JL matrices satisfy, it's invariant under scaling, right? So I have norms everywhere, norm squared of V, norm squared of the projection. I can just divide by the norm. I only care about vectors in the unit sphere. So the property of JL basically only requires this. And I'm going to show that this kind of expression, which, I mean, if you isolate, maybe I can do it on the board, but if you write down the kind of low distortion property for a unit vector, it's basically requiring that this norm of pi b squared minus 1, it's between minus epsilon and epsilon. Is that clear for everybody? Should I? Okay. So I'm just going to expand this. I'm going to show that this is equivalent to a quadratic form in sigma. So if you look at what this pi matrix is doing, well, basically it's making this row vector inner products. And then you have the sum of the squares of the inner products you have for each row, right? So this is what we get. Since this is a unit vector, I can replace this 1 by a sum of the squares of the coefficients of V. That's what I do here. Oh, not seeing. Okay, yeah. Here. And then this square, I'm just going to expand it as a product of 2 terms. And I'm going to use different indices because I want to make all these cross products. So if you expand that, what you will see, it's basically that this is a product of a rank 1 matrix. It's a quadratic form on sigma, but with respect to a rank 1 matrix, which is VB transpose. And then basically here we're removing the diagonal terms. So it's exactly in the framework of this Hanson-Wright inequality, where I can make very precise what this matrix is. It's very structured. Block diagonal, each block, it's a rank 1 perturbation of a diagonal matrix. So just using Hanson-Wright inequality, I can show that the deviation I care about, it's upper bounded by this exponential decaying thing. And in this case, I can compute explicitly what these 2 matrix norms are. I'm not going to do it here, but I can tell you that this thing scales as 1 over m, and the operator norm has the same behavior. So this is what you get here. Then it's just a matter of choosing the right m, so you can guarantee that this deviation probability is less than delta. OK, so now we know we can use the Hanson-Wright inequality for proving distributional JL. What I'm going to do now is show you a new proof of the Hanson-Wright inequality. So I haven't even done the proof of Hanson-Wright. And why do I want to get a new proof of Hanson-Wright? Well, there's many reasons. The most important one, if you have ever seen it, all these proofs at some point use some kind of decoupling step, which allows us to somehow partition this quadratic form in a nice way, getting linear terms, and you can condition on those. So somehow it's trying to reduce this quadratic concentration in something that looks more like a linear concentration. But that introduces some artificial random variables. So basically, you're picking some Bernoulli random variables on top of this quadratic form, and this introduces some extra variance. So there's no way that this proof technique is going to give you something sharp. In fact, most of the proofs of Hanson-Wright do not have any explicit constants on this C that I mentioned before in the concentration. The best we can find in the literature is something that was like 1 over 64. And this C, the lower it is, the worse the concentration. So it really looks bad. It's kind of constant. On the other hand, we want to get a deterministic counterpart of this algorithm. And derandomizing this decoupling is extremely slow. You basically need to enumerate all the possible realization of these Bernoulli random variables. So what I'm going to do now is show a simpler proof of the Hanson-Wright inequality with a constant which is much better. So it's something like 3 over 20. It's much better than that.
Claims the constant is optimal?
It's sharp in a sense. You will see the proof, and I can tell you in which sense it's sharp. I mean, it's hard to say what's sharp here because, let's go back here. I mean, this kind of inequality, it's something that only depends on the operator and Frobenius star. I mean, if you really want to get something sharp, you should use A completely.
Okay.
But in the sense of the dependence of these 2 things, it's sharp. OK, and the proof is quite simple. It's based on this very simple lemma that basically says the following. So suppose you have two random vectors, which are independent, and each one of them is upper bounded in terms of the moment generating function, from one to respect to the other. So you should think of these y's as being the Rademakers, and the z's as being the Gaussians, right? That's what we have. And then what we can show is that for any symmetric matrix with zero diagonal, well, the moment generating function of the quadratic form is dominated by the other. And this in principle is highly non-trivial, but I'm going to show you the proof. It's 2 lines. So how we do this? Well, first of all, you write down what this expectation is. So there's a bunch of independent random variables. And what we can do is somehow conditioned on y2 through yk. And look what's inside here with respect to y1 over. So the expression might look a bit nasty, but basically the only thing you need to observe is that since the a11 term is 0, everything here is just a fine on y1. So basically, this is a linear term in y1, and this is a constant. So you can use the hypothesis and replace this y1 by a z1. Now you can take this expectation with respect to z1 outside, get the y2 inside, and do this sequentially. And that's all. Now, from here onwards, I mean, what we're going to do is basically follow the same strategy for regular Hanson-Wright. So really, this is the heart of the.
Are you really using symmetry of A?
No, I don't think I need that. Yeah.
It's just a zero diagonal.
It's just a zero diagonal. I mean, it doesn't even matter what these signs are, right? Because you know that you have it for every lambda. So
we just need to make the quadratic term vanish. That's the only thing.
Exactly. Yeah. That's all. So I'm going to show you a little bit of how this is done once you have this lemma, because it makes sense. But I'm not going to go through full details here. So what's important from this is that we can replace, I mean, if we're trying to control this probability of deviation with respect to the Rademakers, we can use, again, Chernow's strategy, right? So we get this exponential thing, the moment generating function with respect to this, and then by the lemma, we can replace it by the one with the Gaussian. And now the key thing is that the Gaussian is unitarily invariant, so I can look at it in whatever basis I want. So why not looking at it from the eigenbasis, right? Then by this unitary invariance, I can just look at this and change basis. I get something which is quadratic, but then with a diagonal matrix, right? So basically, I have a bunch of Gaussian squares with the respective coefficients. And now these DIs, I mean, these are the eigenvalues of A. That's also important to observe. So doing this, I get something which is a sum of independent random variables. I can turn it into a product, and I can explicitly compute each of these moment generating functions, which gives us this. And now you see why the operator norm becomes important, right? I mean, these are the eigenvalues of the matrix. Whenever we reach anything beyond 1 over the operator norm of A, we're going to run into this thing diverging. And we can also write this alternatively, since these are the eigenvalues, as a certain determinant dependent of A. So I should say here at this point, once you have this inequality, I mean, once you replace this thing over here by this determinant, you get something which is completely independent of the distribution. So it's just a matter of optimizing this thing. In fact, if you just use this kind of quotients that we have in this product over here, and you upper bound them by a appropriate exponential function, which is what's typically done for the concentration of chi-squared random variables, you can just follow the standard proof, and you'll get Hanson-Wright inequality with constant C equals 1 over 8. So that's already much better than this 1 over 64. So what we do here is do a little bit of work in terms of how we can optimize this thing with the determinant. You can get something which is much finer, and we call this a determinant lower bound. But it's not very important. I mean, you just do this and then optimize the lambda, and that gives you this kind of concentration. It looks a bit more complicated than the standard Hanson-Wright, but let me just tell you, you can dominate this thing by the standard form of Hanson-Wright, and the constant you get is this one I promised. So 1 minus log 2 over 2.
And every term in this exponent is tight.
Say again?
The terms is tight, basically.
This one is tight, yes. Yes, but then if you want to turn it into a regular kind of Hanson-Wright expression, you can do so with this kind of constant. So any other questions? Okay, great. So now let's turn to the question of sparsity. Of course, replacing Gaussians by Rademachers is a significant improvement, but we still end up with a matrix which is dense. And we would like to sparsify it so we can get a faster embedding. Now, the bad news here is that it was proved that for independent entries, this sparsification is only going to buy you a constant factor. So I don't know the exact constant, but I think maybe 1/3 of the coefficients can go away, but not much more than that. So that's what Ecleoptas proved, and Matuszek got a lower bound. Unfortunately, there is a way out, which is trying dependent entries, and that was proposed by Kane and Nelson. So the idea is that here, we can think of this as basically the same distribution we had before with these IID entries, but now we select a random subset of size S. And we can do this in two ways. Either we can pick a uniformly random subset, or we can partition in blocks, in S blocks of size M divided by S. And in each of these blocks, we just select one coordinate uniformly at random. So for a certain column sparsity parameter, we choose S, that I'm going to specify in a couple of slides. All we do is coming up with a way. So you can think of this sparse construction as a two-step process. First, you select a subset of coordinates you want to maintain. So basically, this is the masking matrix. And then only for those coordinates, we're picking this 1 plus 1 minus 1 random realizations. So in fancy linear algebra notation, this looks as a component-wise or Hadamard product of these two matrices. And now the scaling factor is slightly different. It used to be 1 over square root of m, but now since we're only selecting S coordinates, it's just 1 over square root of S. So the analysis is quite similar, and not going to go through the details, but the point is, even in this sparse case, you can pretty much do the same kind of arrange in terms of turning this deviation as a random quadratic form in the same vector sigma. And this kind of block diagonal matrix we used to have, it's almost the same, but now each of these vectors B are sparsified by a different row of the masking. So is all this setup clear until this point? Okay. So the point is that basically we can follow a similar argument as was done in classical JL. So I'm going to set the sparsity to be epsilon times m. So basically, we have m coordinates per column, and we're selecting an epsilon fraction of them. And then if you assume that we have high probability, you have these two upper bounds, you can condition on that, and then just use the regular Hanson-Wright. And since we pick this S to be epsilon m, these two terms over here are balanced. So the kind of concentration we get is something like 1 over c to a certain power. So this is vanishing as with the number of input vectors. And all we're left with is proving that this event star happens with enough high probability. Now, this involves two kind of bounds for this matrix we define here. However, the part regarding the operator norm, it's very easy. So not only with high probability, it's for sure that the upper bound of the operator norm is bounded by 1 over S. The part regarding the masking is much more difficult, or I mean, significantly more difficult in comparison. And if you just write it down, you get this kind of expression. So what we're looking at here is somehow a sum on the different pairs of columns of these expressions that are scaled by the coordinates of V. And this QJK, it's a random variable, but it turns out that it's a sum of non-independent random variables. Okay, and I'm going to explain right next why this is the case and what's basically the meaning of this thing. So what's happening is that this QJK random variable what it's doing is looking at two different columns, J and K. And here I'm denoting this X by the selection of the masking. So suppose that the sparsity here is indeed 1. Right? So we're just selecting one element per column. And here there's a random realization for these two columns. So what this QJK random variable denotes is basically counting the number of collisions within these two different columns. Right? So we're just basically going through here and seeing what are the coincidences. And in this realization, in fact, we have no collisions, so the Q is 0. But in general, it could be something else. Of course, it's always going to be upper bounded by S. Now, you can see why this thing is not independent, because we're choosing a random subset in each of these. However, it's clear that this thing, the dependence goes in the right direction. We have somehow a negative dependence in this random variable, in this sum of random variables. Because, for instance, if the sparsity is 1, and I tell you that I selected here the first coordinate in column J, well, you immediately know that everything else has to be 0. So that's what I mean by negative dependence. Whenever I know that I picked a coordinate, that immediately makes everything else less probable. And when you have this kind of negative dependence, you can basically go through with the same argument. You just replace these dependent random variables by their independent marginals. And then you can sort of use the same kind of concentration argument. And I'm not going to do it here because even from here, it gets a bit technical, but I think this is the heart of what's going on. OK, so now let's go into the derandomization business. So first of all, in certain settings, it's of course preferable to get something deterministic as opposed to random. And there's many reasons for that. For instance, I mean, the guarantees we get with distributional JL hold with high probability, but we might want to prefer something that holds surely. On the other hand, of course, a deterministic algorithm will not be sensitive to these random fluctuations that we're picking for our projections. There's this hope that this I'm not sure, and I don't have any theorem for this, but I would like to see whether, for instance, these deterministic constructions do a better job exploiting the structure of the input, as opposed to this distributional JL, which is completely oblivious to the input. And of course, also there's conceptual reasons to think what can be achieved with randomized versus deterministic algorithms. So let me just in a nutshell explain what's our basic algorithmic principle, which is based on the method of derandomization by conditional expectations. So suppose we have a randomized algorithm which depends on these independent random outcomes, x1 through xk. You may think of this as the Rademakers, for instance. Right? And our deterministic, our probabilistic guarantee looks like this. So some sort of expectation of a certain function, upper bounded by a confidence delta. So you should think of as basically being the event of half-equal distortion. Then, I mean, we can write this big expectation by integrating with respect to the first random variable and just using a probabilistic method kind of argument to say, if this integral is less than or equal to delta, their mass x is a realization of x1, which gives me the same kind of expectation with respect to the rest upper bounded by delta. And I can just repeat the argument. And then in the end, what I find is a deterministic assignment of these x's. Of course, this is only going to run efficiently if we can compute these conditional expectations efficiently, which is typically not the case. If you think about these Bernoulli random variables or Rademakers, you'll have an exponential number of realizations. However, there is no need to do this if we can properly upper bound these expectations. And this leads us to the idea of pessimistic estimators. So the idea here is that there's some parameter space P, and for each of these parameters, there's an associated distribution, T of P. And we will say psi is a pessimistic estimator if it's for any possible distribution dp. The probability of the event we care about is upper bounded by this psi function. So the very high level idea would be that somehow use this, some sort of potential function, right? So we start with a distribution that guarantees this probabilistic state. And then we somehow traverse the space of parameters x and using different kind of p's that relate. So basically what we're doing is fixing partially these coordinates, and this leads to a number of distributions, and we end up with something which is fully deterministic. But whenever we do this, we do it in such a way that we can control this failure probability. Okay, and you can imagine that somehow, if this psi, for instance, is concave, this will allow me to pick a proper derandomization at every step. So let me explain very simply how we can, for instance, derandomize the Hanson-Wright inequality using pessimistic estimators. So here our space of parameters will be, so remember that we have these vectors x1 through xk, there's this matrix A. So our parameters are basically indexing what things we have fixed and which we haven't yet. So there's a vector of length k, which can be either -1, 0, or +1. What's happening with this vector, I mean, the distribution will pick according to this parameter, d of sigma. It will be such that its marginals, when the sigma I is 0, is going to be a Gaussian. And when you fix one of these to be either +1 or -1, we're fixing that zi to be that value. The pessimistic estimator we will use is based on the Chernoff inequality. So basically, since we know that the failure probability is upper bounded by this, we can just use this as a proxy. And what's important to show, of course, is that you have this concavity property. So basically, whenever you have a partial assignment of sigma, and there's a coordinate which has value 0 currently, so we have a Gaussian there. If you choose an assignment of sigma I to be +1 or -1, these two on average are not worse than the original psi. So basically, one of these choices is as good as the psi of sigma. And then we can move on. So in very simple words, this derandomization is based on that idea. So we start with having no idea how to pick this sign. So we have all Gaussians, and we go by one, minimizing this psi potential. Now, a few technical comments, because I mean, you need to compute this pessimistic estimator, right? And this looks as this moment generating function. What is shown early in the talk is that this kind of thing, when you have only Gaussians, it looks as a determinant of something. And even when you conditional things, you still get this kind of expression. So basically, computing this psi will require some algorithm for computing determinants, say, for instance, SVD. So even if you try to make this faster, you're not going to get linear time. However, for the case of JL, things are much better. Because our matrix, it's a block diagonal matrix, where each block is a rank 1 perturbation of a diagonal 1. So computing determinant of a diagonal matrix is trivial, takes linear time. And doing this rank 1 update, we can use this Sherman-Morrison formula from linear algebra that also allows us to do this in linear time. So the good news is that we can run this efficiently for, I mean, not only efficient, but linear time in the case of JL. And we end up with an algorithm that runs in this time S times, so N and Z of V in this case is if you pick your whole input, all these vectors V is counting the total number of non-zeros of those vectors. Right? So it's the sum of the sparsities across all input vectors. And under the mild assumption that this number of non-zeros is at least as large as the dimension, we get something which has complexity S times N and Z of V.
You're here referring to the sparse version of GL, like S.
Oh yeah. Right. Because otherwise you'll get M here. You'll get the full number of rows. I'm thinking about when you already made this masking, so you get this P number of, and then you have S times D of them. Right? Now the masking is a bit more technical, and I don't know how much time do I have. Like 10 minutes. Okay, so I'll be.
It depends on how much.
No, it's not that long, but I want to show some numerical results as well. So so the faint-lived distributions for the masking is of course a bit more tricky because I said that things are not independent. But in fact, we can pretty much ignore that, and it kind of works as well. So our space of parameters is basically a matrix, right? So where we have this masking matrix, which is 0, 1. what we're looking at here is the probability of selecting a certain coordinate. So this PRJ represents the marginal probability of making that choice, of taking this coordinate. As I said, in the K-Nelson analysis, these choices are not independent. We have these constraints, right? So for every column, we're selecting S coordinates. But what we can do here is basically we can start with this space of, we're going to start with this P being all equals to epsilon, uniform choice. And we're going to somehow traverse this polytope, making deterministic assignments one at a time. So if you're familiar with the technique of pipette rounding, by any means, this is very similar. So in fact, we use independent marginals, and somehow we traverse this polytope in such a way that we don't violate these constraints. So, okay, I don't want to go too much into details on what this is, but basically this is what you get using Chernov's inequality in the event that you want to control this Frobenius norm. Right, so that's what, remember that event we wanted to control with high probability was this Frobenius norm of A was upper bounded by something. So this is basically what we're writing here. We just use Holder's inequality so that we can make things nicely decoupled. So we instead of taking products inside of this expectation with these different choices of columns, we just use Holder's inequality and we take these as exponents. And basically what we end up doing in the algorithm, it's a very simple idea. Let me go to the board and just make a quick drawing of this. So we have this masking matrix, right? This has m rows and d columns, right? So we know that. And what we're going to do is partition the space of rows into S blocks, right? Here. And each block, of course, will have size m divided by S. So what we'll do is de-randomize by blocks. We're going to pick the first block. We're going to compute the pessimistic estimator here for every possible choice. And we're going to stick to the one that minimizes the potential. That gives me some choice. And then I move on to the next block. I do the same. So the whole point is that I can do these updates fairly quickly. And also, of course, there's a point that this pessimistic estimator has to be concave on the blocks. So every time I have a partial assignment and I want to make an update, I make these finitely many choices. Since the pessimistic estimator is concave, there is one choice which is as good as what I had before. And yet again, there's some technical details that happen here. Computing this thing in general is expensive. So what we do is there's a choice of a particular input vector set, which is basically all differences between different canonical vectors. And this we call the universal masking, but it's also present in the K-Nelson work. They call it the code construction. And if you make the assumption that your input is sufficiently large, then your running time is guaranteed to be of the same order that we have for the signing. And in this region, what we get is basically the same running time that you would get just with the randomized assignment and then making the matrix vector product. So what we get all in all is this deterministic guarantee for a given input vector set. So we maintain low distortion. We have the guarantee of the projection proportional to what you get with standard JL. And the running time it's the same what you would get from the K-Nelson analysis. So how much time do I have now? Like 5? Okay.
So I have a question. This stuff with pessimistic estimators, is that something standard for de-randomization, or is that something that you developed?
It's one of the, no, I would say it's fairly standard. I mean, not many people know about, but if people that work in de-randomization, they certainly.
That seems really powerful.
It's powerful, and I like it because it's very natural. I mean, you can turn these probabilistic proofs into algorithms, and that's very beautiful.
It's by Prabhakar and Spencer.
Okay.
Yeah, that's from the 80s, right?
Yeah.
And there have been many works on.
Right, but the original idea is due to Prabhakar and George Spencer.
In fact, there is a version of JL which is based on this method of pessimistic estimators, we realized after we were done with this work, but it's kind of the same idea in the dense setting. The analysis is much trickier though.
That's RMN, right? But
I think so. I can't tell for sure, but
your manager did something much simpler.
Oh, okay.
You're going to ask Shiva.
so let me quickly go through some numerical results, and this is very preliminary work. I should tell you that this semester I'm teaching a machine learning course, and I got this end of the semester project for my students. So they carried out these experiments, and I got them last week, so I haven't checked all details, but just want to show you a little bit how this looks like. So what we do is we get this randomly generated data in dimension 500, and we have 1,000 input vectors. So you want to maintain the distortion of those with an epsilon factor, which is 0.2. If you use the JL statement we had before, this roughly tells you that the dimension projection is like this, 175. So one of the questions we were wondering is whether the randomization is much slower. So here there are a few results with this instant size. You can see that the random algorithm is pretty quick. It takes like 20 seconds. The deterministic one takes like twice as much. But they haven't completely optimized so all these tricks I told you of doing things very fast, they didn't test them. So for instance, they use SVD for computing the determinants. So I'm still surprised that this works in these many dimensions. But you can see, for instance, okay, the success probability you get with the random one, of course, is going to be lower. But I'm a bit surprised that it's this low. So they also carried out some.
So is that computed empirically, or is that basically?
It's computed empirically. So basically, right. So your construction is completely oblivious, and then you can evaluate the frequency of things that were distorted.
Mm-hmm. But depends on, like, I mean, you have m equal to 175. How did you split that into epsilon is 0.2? You said.
Yeah.
And what is the delta?
There's no delta here because you're.
No, for random.
Say again.
For random.
Measuring it empirically, I think.
Okay.
Yeah. That's what I'm saying.
So you didn't take like 3 runs and take the median or whatever?
No, this is for particular realizations, and then you compute the frequency of things that were distorted or not. It's super simple, yeah. and then you can make some box plots with more. So here there's 20 realizations of this thing. So most of the time it goes pretty well, over 95%. That's what I would expect, right? But every once in a while you see this, this much lower kind of performance.
So the random instance, is it easy or hard for like JL?
What?
So the instance you gave is random, right?
Right.
Is it easy case or a hard
easier,
case?
or I would expect easier. But
that's what I would expect.
But I don't know.
Case, so
Yeah.
Right.
But
maybe it's the same. Maybe it is the hardest. I don't know, because it spans everything.
Right.
Like it's kind of.
I see it's
because it's full. Maybe you would expect things which are in lower dimension to be actually easier.
Right.
So I don't know.
Okay.
so for instance, in this example, what we did is, so there is this 500 dimension, but the vectors are actually supported in the first 175 coordinates.
Right.
So one of the things that I wanted to test is whether this deterministic algorithm will figure that out. And it didn't. I mean, I'm not sure. So the results weren't very conclusive in that sense.
I don't know if it matters for the comparison between the techniques, but it's probably the hardest set for
Right,
this, but for comparing deterministic versus randomized, maybe.
like maybe for easy set randomized will get it 99%, right? It's possible.
Maybe.
That's what it is.
So yeah, what else? So here are some pictures if you're just wondering how this looks like. So first you see the random projection, and second one is the one we get from the deterministic algorithm. So maybe you can't see from this far, but the first block of the deterministic one looks kind of a bunch of diagonal things. And that's because the pessimistic estimator is kind of greedily optimized. So in the first block, it looks pretty structured. But then from then onwards, actually also in the first few columns has this similar kind of behavior.
You don't see the first block certainly, but
No, you can get close if you want.
okay,
But it
yes,
looks
yes.
kind of like a bunch of diagonal things. And then, yeah, it looks more structured in a sense, but I don't know how to,
Yeah.
interpret this really. Just to show you how it looks like. Okay, so all in all, let me conclude by saying, the dimensionality reduction it's a key primitive in data analysis, and the JLemma allows you to do this dimensionality reduction quite fast, right? So what we do in this work is basically show that you can do this deterministically, based on these ideas from randomized algorithms, and we can basically reach the same performance. And there's this new kind of technical contribution, which is based on this new proof of the Hanson-Wright inequality. So a few open problems. Well, first of all, we're not very happy with this assumption that the number of non-zeros is sufficiently large, and we believe this is not necessary. But this would would require something, arguing in a smarter way than using this universal masking, something which is more instance dependent, right? Also, there's a question, you asked at the very beginning, right? So JL transforms are usually used in online or streaming settings where you want to be completely oblivious to the input, right? So we hope that maybe there's a way to argue about some sort of online settings where you can maybe regret some of your decisions along the way, fixing things so you can still do good projections. Finally, there's this super interesting question about deterministically constructing RIP matrices. So if you've ever heard about this, well, so these RIP matrices are basically things that keep low distortion, but on the set of sparse vectors, and that's an infinite set. So I don't expect that these ideas will kind of directly resolve this. This is a very hard question, but I think it's very interesting. It's something that is good to keep in mind. So with this, I'm done. Thank you very much.
Okay, thank you.
You mentioned some applications of dimensionality reduction, and also just in this algorithm, are there any candidates for just particular algorithms or settings where this might improve the state of the art? Or
let's think. So for me, the most important thing is whether you want to be oblivious or not. So in settings where you don't care about being oblivious, then I think this can certainly help because it gives you guaranteed low distortion, right? So it's more a matter of what's really your setup. So I'm thinking maybe in some kind of machine learning application where you already have your data, maybe you want to go with this because it takes roughly the same time as the randomized one. But typically for streaming settings and online, then, as this is, it's not helpful.
And the only part which uses these non-oblivious is the derandomization, right? The one, or is...
So let me say the masking, for instance, it's, since we are doing this universal masking,
okay,
it's completely oblivious. So the point is that this universal masking works for any kind of input,
sure,
in the right dimensions.
Okay, I see.
But then the signing,
I see. So that part of
that's
of making things deterministic is makes it non-oblivious.
Right. So there is some hope that we can resolve this online question in a meaningful way because at least part of the algorithm is oblivious in a sense.
So does it follow then? So for online you can get fast and sparse, but not deterministic. Fast comes from sparse, but
sure.
So you can get that part, but not the deterministic part. Is the part that's
right,
clear.
Right. But that's Kane-Nelson.
Right,
That's
okay. Good.
Well, can you also? Is it reasonable to compare it with these techniques where you don't care about the sparsity of the matrix, but at the end of you care about the fast computation, the fact that you can multiply by the matrix
fast Fourier transforms?
Yeah, like you would usually use Fourier transform as part of the multiplication, but you can do other things.
We tried this, and I think that somehow these results are uncomparable. So the regions where fast Fourier transform is better, but there's others which this sparse thing is better. So for instance, the Fourier transform constructions do not exploit the sparsity.
But then there are these things that are multiplying in N and Z. You mean they don't run in N and Z?
They don't exploit the sparsity of the B vectors, the input.
Yeah, the what you call the N and Z parameter, right? I thought there are. Isn't this whatever maybe Woodruff and Clarkson did?
Okay, maybe I'm wrong about that, but I thought that at least I was looking at older works. So this Island and Liberty, these other works, they don't exploit the sparsity. But I have to say I'm not.
Let's thank Cristóbal again.